Thank you for the introduction, and I want to thank the organizer for inviting me and organizing this nice event. And I must apologize because there will be no fluid equations in this talk. It will just be a very simple system of linear PDEs, but it is strongly motivated by some certain coupled system with fluids. So in fact, it's a toy model. And when we started to work on this a couple of years ago, somehow plan was to solve this toy problem in a week or two and move on to real problems. And several years after, I hope preprint will be out in next week. So it turns out to be very interesting and rich problem. And this toy problem, I will try to convince you, is the real toy problem in a sense that really captures the conceptual difficulty of this problem. So I hope now we have a good understanding to really, after this, tackle the problem that motivated us. So what motivated us? It's fluid structure interaction. So we already heard several talk about fluid structure interaction, and also Anna's talks before mine. So there are a couple systems of fluid and solids. And I will not talk about application, but there are many applications. You can look around and you will always see some examples of fluid-solid system. But what I want to emphasize here is that mathematically, they are described as PDE system of hyperbolic parabolic type. And then they are not coupled on the whole domain, but you on part of the domain you have hyperbolic system, and part of the domain you have parabolic system, and they are coupled over the interface. Okay, and now I will proceed with several very trivial and simple observations just to motivate what we are doing. This is really on the undergraduate level. So let me compare Cauchyan periodic problems. So in principle, when we have Cauchy problem, like always, we give initial data, we give right-hand side, and we solve for a solution. When we are solving for the periodic problem, we give some time period t. We give some time periodic force, and we want to find a solution which is time periodic. And of course, we can write formulas in all these systems. So this is for Duhamel formula for this linear system solution. And you see, now you already see the difference. When we want to solve time periodic problem, we don't know what are the initial data. So we need to find initial data. So what we do, we can plug in x of t here, write x of t, capital T equal x of 0, and we get this kind of equation. And you see, again, that somehow flavor of the problem is different, because in principle here, we need to invert this operator, which is not always easy things to do. Okay, and let me proceed with another simple example when there is no periodic solution. So let's consider just a harmonic oscillator. And we know all what is the general solution. And we say that natural frequency is 1, because if you don't force it, it oscillates with frequency 1. And if you add some forcing, you have this explicit solution. And if forcing is of frequency, has a frequency omega, you see when omega goes to 1, it blows out. And this is called resonance. So if you hit your equation with forcing with natural resonance, you have unbounded solution. Saying in other words, so if you have periodic forcing, but no periodic solution. Okay, and what I want to emphasize here is that if you add some damping to the system, resonance will not happen. So damping will destroy resonance, and even if you force it with natural frequency, you will always have unique periodic solution. This is just one example, so prove by the example. Okay, so moral, if there is damping strong enough, there is no resonance. And of course, this is not just for ODEs. One can simply extend this also for PDE. So let me just show it for the wave equation. So let's say we have wave equation. We force it with some time periodic forcing. We can plug in the following ansatz, and we get this equation. And then we can, of course, since this is, we can take orthonormal basis in L2 consisting on L2 functions, and then we can write down equation for Fourier coefficients. You just expand it in Fourier series, and you get this equation. Again, you see what? If you force it with some of the natural frequency, and here natural frequencies are eigenvalues of this operator L, you will again not get a formula for the Fourier coefficients. You will as you approach this frequency, you get unbounded solution. So okay, and also the point is here. So also in this kind of equation, resonance can occur. So if you force the equation that oscillates at natural frequency of the system. And here also I want to emphasize, if you add some damping, for example, this kind of damping, again, you can easily see there will be no resonance, because you easily see what you will get here in the equation. You will have some imaginary part, and you will never hit zero. Okay, so these are two simple examples which show us that in principle, time periodic problem is not well posed. So if you have time periodic forcing, you can still have, you don't necessarily have periodic solution, and there is this, and then you have usually unbounded. So there is this dichotomy. So you have time periodic forcing, either you have time periodic solution or a resonance occur. And what also we saw in this very simple example is that somehow when you have dissipation, then you will have time periodic solution. So somehow in the wave equation with zero forcing, you have many time periodic solution, because it's a wave equation, so you have all these cosine signs. But in principle, if you hit the right frequency, then you don't have a time periodic solution. Okay, and now let's go back to the time periodic fluid structure interaction problem. So what is we are interested in a weak solution. And in a weak solution, what you work with energy inequality. And why this unbounded solution does not contradict energy inequality? Because when you have some energy inequality, d dt E of t equals 0. And for Cauchy problem, you integrate, you get some information. Here you integrate from t to t, and you get just 0 equals 0. So you don't get anything. And of course, if you have some dissipation, then you get something. You get some boundedness, like here. No? You get some estimate, but it's not enough usually, because you don't get you just get estimate from dissipation, but not from energy. But the point in fluid structure interaction system is they are coupled. So in principle, let's say you have some big domain, and then you have, let's say, omega s. Here is a structure. Here is omega f. So dissipation is acting here, and from this term you get some estimate. But there is no dissipation here, so you don't get any estimate here. So if you want to get something, you must somehow go through the boundary. So only way to get the estimate is to go through the boundary. And that's the reason there are very few results in this direction. I guess after my talk, we will hear Andre talking about this result. And there is also result of Sebastian and his student Claudio Mindrila. This is existence of weak solution. But I was surprised after searching literature, so there is no theory. So only attempt of general theory is this paper from Galdier collaborators. Actually, it's a very nice paper, and I will say a few words about this in next slides. And there is also some result about with Filippo Gazzola and collaborator about various partially dissipative plate models. Okay. So, but the point is that this estimate, which I said, has to go through the boundary. And this is in some sense reminiscent of observability estimates in control theory, because what you have? You want somehow observe only a non-fluid domain, and you want to estimate everything just as observing fluid domain. And of course, then you expect some geometric condition to come in, because somehow here you have a finite speed of propagation, this information, and also you have some characteristic. This information will go through boundary into this part. But Here, for example, we expect that information will reach every point, but in some other geometry, we do not expect such a behavior. So this is the state of the art, more or less. And let me just say a few words about this theory, what they call partially dissipative systems. So in definition, partially dissipative system is just this. So let's X be a Banach space, and then A be generator of C0 semigroup of contraction, and Ft periodic system. So it's very general. This is what is called partially dissipative system. And there are lots of nice results there, but I will summarize this in a few lines. So this is interesting. So we said what was the, from example, what was the intuition? So we say wave equation does not have periodic solution necessarily for all right-hand side. Heat equation will have it. And here they connect it nicely with stability properties of the operator A. So if a semigroup is uniformly stable, i.e. we have exponential decay of solution, then for every right-hand side in this space, there exists unique time periodic solution. And second result, if semigroup is only strongly stable, so the solution decays, but there is no rate of the decay, then there is a unique periodic solution for a generic right-hand side. More precisely, if you have a right-hand side in some dense subset of L1 to X. No? And the point is there is no characterization of this set. It's go through some ergodic theory, so somehow you cannot get from this result characterization of this set. But now the question is, in which case are we? So is this first? Because if this first theorem applies to our case, then everything is solved. But unfortunately, we are not in this case. Or fortunately, how you want to look at it. We are in this second case. And that's a result from Zhang and Zuazua from 2007, where they consider this parabolic system, the heat wave system. I'll introduce it here and show they are not uniformly stable. They're just strongly stable. So we are in this case. And what was also interesting that if certain geometric conditions were satisfied, they call geometric optic conditions, then you still don't have uniform decay, you don't have exponential decay, but for a smooth initial data, or at least in generator of a semigroup, you have some rational decay. So you are not, it's still, in this geometric case, it's still better than just strongly stable, but it's not uniformly stable. So this is the result of Zhang-Zuozua. So let's see what is our equation. So our equation is basically, can resonance occur in this hyperbolic, parabolic system? And we still don't have full answer, but I will present partial answer and what do we expect. Okay, and now finally let me present you this simple linear system we are studying here. So we call it heat wave system. I just, after a few years, I just realized it's a nice name, which maybe have different implication in not just coupling heat wave, but as a heat wave. Okay, so what we do? In part of the domain, we, instead of Navier-Stokes equation, we just have heat equation. So big simplification. Instead of elasticity equation, we have just the scalar wave equation, another big simplification. And we have following coupling condition. So what I call gamma. Gamma, I call this interface between fluid and the structure. And coupling conditions are, okay, this is just continuity of normal derivative. Because also, I wrote it not in this general configuration, but in a rectangle. So what, sorry, this is maybe, actually this is where I wrote this system. So in principle, this should be normal, they're not a y derivative generally. And this comes from the equality of stresses. Because if you think what is stress tensor of the wave equation and heat equation is just gradient. And this is, okay, a bit maybe unusual on first sight. It's not U equal V, so it's not continuity. But when you think about our motivation, it's clear, because U is displacement, V is fluid velocity, at least in our motivation. So this means our velocity is continuous over the interface. Okay, so this is our system, and all we have is this energy estimate. So this is what we have. And this is just on the fluid part. So this is just on this part. On omega s, we don't have anything. So we have just that H1 norm is bounded. This is what we formally get. Even though we even don't get this. This is just formally, because you need some Gronwall. So in principle, you cannot even get this, but morally we have this. Okay. And then I will just state the result on just 2 instructive examples. And then in the rest of the talk, I will comment why I choose these 2 instructive examples. How can you generalize? Because the result hold more generally, but it's easier to state these 2 examples. So one example is what we call it inverted ice cone. So it's like this. You have, this is the full domain, but then you have a semicircle here, and this is omega s, and this is omega f. And gamma is this semicircle, is exactly this boundary. And then the result is if F1, this is forcing of the fluid, it's H3 in time, L2 in space, and forcing for the fluid is H6 in time and L2 in space, there exists a unique time periodic solution to heat wave problem. Okay, this is the first result. Second is this rectangle. So sorry, omega s. For some reason, we always like to structure be above. And then, surprisingly, this is a more difficult case. So we lose here more. So here, numerology is 4 and 8. Okay, now let me comment on this. First, what you notice, it's if you do weak solution, these are lots of derivatives you are asking for. No? Much more than in a Cauchy problem. But also I want to notice that somehow, of course, this is dense in L1, L2. So this is somehow in line with Gaudi's theory I presented before. So but now we have characterization of this set. Whether this is optimal, we do not know. But we suspect it is almost optimal. Because first, what you are probably concerned is why we need so many derivatives. Because in Cauchy problem, we don't need any time derivative. We will real gain in regularity. And let me present you. First, notice that loss depends on geometry. Here we lose more than here. But this is somehow it's expected to depends on geometry, because somehow you, as we said before, it's information must from this boundary come to the interior. So and also, so it depends how geometry looks. Okay, let me just again present you another very simple example, which shows you that you cannot think about this problem as a you cannot use your intuition from the Cauchy problem. Somehow you expect difference. So let me just construct explicit solution again. Here in the rectangle case, we define UN like this. So we here takes a solution to the wave equation in 2 dimensions and just just localize it in some strip here. Why we localize it? Because we don't want it to influence the boundary. And again, okay, so no. And then UN is the solution to this wave equation, and also to the coupled system. Because since this is 0 on the boundary, we can take solution to the heat to be 0. So we have explicit solution. And now we can play with, since it's a linear problem, we can take a solution in terms of series, and we can play with these coefficients. But the point is, we can cook out any kind of the solution. We can cook out solution which is L2. So if right-hand side is just L2, not more, then the solution will be L2, not more. Also, we can take some more regular solution, but it is not still weak solution. But so weak solution, we should take this kind of regularity. So we should take at least H1 for the right-hand side. So you see, we really cannot gain any regularities in the Cauchy problem. We really need, we lose something. But also, my point is here that, okay, this solution, it's obviously not weak solution, but if there exists a periodic, we would like to call this periodic solution. Everybody would call it periodic solution, even though series do not converge in suitable norm. So this is also a point to remember. I will come back to later. So, but the moral of the story is, yes, you expect some loss of the derivative. Okay, you can complain, here we don't lose 3 or 6, but we have, this is a very simple case. We have exactly identify when we lost derivative. We cannot prove it's unavoidable, but we suspect it's more or less unavoidable. Okay, so let me just say a few words about proof. Okay, I cannot have lots of time. So the construction is it's not so unclassified. So we add this to the wave equation, regularizing terms. So basically we have two parabolic equations which are coupled. And for this there exists an abstract theory which gives us immediately a time periodic solution. So the crucial step is to, and these are regular solutions and they have nice regularity property, like this, like our Cauchy problem. And the crucial step is to derive the estimate which does not depend on solution. So, and again, I want to emphasize this, the point is to control norms of V through the coupling condition. So this is the whole point. And how to derive this estimate. So first key observation, and just to return, so this is reminiscent of boundary control problems. So there are works with very similar estimates, but in this context, there are many works. This is, I think, very classical in control theory. But we were able to expand this somehow generalize these classical estimates, again, because of very specific contexts we are interested in, of time periodic solution. And crucial observation is we can take time differentials for free, in a sense, because it has some flavor of elliptic problem. In principle, like in Cauchy problem, when you take time derivative, you have some compatibility condition, you need additional regularity. Here, you just take time derivative without any conscience. So every integration by parts you can do however you want, it's everything cancelled. So this is big advantage. So time differentiation is completely free, it doesn't cost you anything. And that's why we somehow, if you notice the result, there is no regularization in space variable, but in time we can really use this additional regularity of right-hand side. And there are two estimates. First is classical equipartition estimate. So for the wave equation, when you just test wave equation with a solution, and it tells you more or less if you have estimates for dt, you have estimates from the gradient, and vice versa. So this is first ingredient. This is also very classical. And in classical control theory, you have this, it's called h.grad usually, estimate, and you estimate wave equation with this term. So some linear function times gradient. But for this, you need so-called geometric optics as is satisfied. And one of good characterization, not characterization, but sufficient condition for this geometric optics is so-called star complemented condition. So that's why this is good, because what you need? So you need the following. Let me draw a picture. So for example, you can ask why we didn't take this ice cone. Why we didn't take this? Because this doesn't satisfy geometric optics. Because somehow here, this tangent is parallel. And this prevents geometric optic condition. Because there is this star complementary condition which says that geometric optic is satisfied if there is domain, here like this, which is star-shaped, which shares this boundary, and that whole domain is contained in the complement. And here, this will be not star-shaped because of this parallel condition. That's why this is a harder case, and this is not covered by this classical control theory estimates. And also this is not covered for the same reason. But this is covered because we take just x0 here and everything nicely works. And the idea was also, so first we were looking at the rectangle, of course, and we can solve it with this. This is somehow the degenerate version of this multiplier, which is not good for control theory, but in our case it works. Okay, And what was now a second generalization? So we say, okay, we don't have to take straight lines. We can take a general vector field and estimate along these lines. And I will now finish just to say, okay, so this is the classical control theory. We call it generalized optics because B is not just linear vector field, but it's any vector field. And we also derive this generalized graph condition because it's basically you need to have some kind of Poincaré inequality satisfied. And I will not talk more. I will just show you nice equality. So if you have wave equation which satisfies Dirichlet and Neumann boundary, homogeneous Neumann boundary condition, which is of course ill-posed. But let's say we have such a function, we have this very nice identity. And from this identity, we can derive estimate. So, and let me just show you that. So I started with this example, but we have, with this condition, we can treat quite general domain. We can treat these horns with curved horns. This we call, you see, this we call general graph, because in this curved coordinate system, this is subgraph, no? Because this is sigma and this is then subgraph if you are flowing like this. And also, if you think about now generalization, for example, linear elasticity, of course, then it depends on material how this wave propagates. But in principle, this can be treated with this technique, just it will be more calculation. And now let me just finish with two questions. So now, so we have resonance cannot occur under certain geometric condition and under certain regularity. So can resonance occur with low regularity forcing? So question is probably no, because so answer is probably no, because as this and as this example suggests, it's just matter of rightly defining notion of weak solution. With a low regularity, you will have some solution, because in principle, if you have solution, you can integrate the time differential to get another solution. So you can go up and down in regularity. You have to be a bit careful with constant, but you can do it. So in principle, we have this notion of very weak solution. So with low regularity, we get some weaker notion of solution. So but existence of the geometry where resonance can occur, this is more interesting question. And I would say probably answer is yes. But we cannot prove. I will just draw one picture and I'm finished. So I had a student, master student, just to do some numerics. And she did this, what I called Tetris domain. And here is omega s, here is omega f. And what she tried, so let's put forcing here. And let's put resonant forcing, but the resonant forcing, which is somehow concentrated in this strip. And numerical result, it seemed they showed resonance. Of course, it's just master thesis. One have to test this numerics carefully, so it's just indication. So one cannot be sure, but it's indication that probably in this, if geometric conditions are not such, maybe resonance really can occur. But this is just hypothesis. Okay, thank you for your attention.
I will push my question to break as well.
Okay.
So thank you, Boris, again.
Thank you.